And this is our part 1 report, and this is our diagram. From this diagram we can find out the flip-flop inputs. For example, DC is the XOR of the C and B, and JB is the A prime, KB is 1, JA is connected to B, and KA is connected to 1. At this circuit we are going to use D flip-flop and JK flip-flop, this is the D flip-flop characteristics table. When D is 0 and next state will become 0. And for the JK characteristic table, when the present state is 0, we look at the J for is 0 or 1. If Z is 0, then the next state will become 0. If flip-flop is, if Z is 1, then next state will become 1. And when the state is 1, we based on the K, which K equal to 1 and next state will become 0, and K equal to 0, next state will become 1. And this is our table. When state CBA is 0, 0, 0, we look at the D. For the we can calculate that by using the flip-flop inputs equation. For example, DC is based on the B XOR C. B is 0, as C is also 0, then D is 0. JB is equal to A prime. A is 0, then A prime is 1. KB is 1. JA is B. B is 0, then JA is 0. KA is 1. Then from this flip-flop input, we can find from the flip-flop input and the JK characteristic table, we can find that D is 0, DC is 0, then next step C is also 0. JK of B is 1, 1, then it will become 1, and JK A of A is 0, 1, then next step of A is 0. Then from this next step we go to the 0, 1, 0, which is here, and we use the same ways to find the next step, which is 1, 0, 1. Then after that we will find a loop back to the 0, 0, 0, but two of the step, which is 0, 0, 1 and 1, 1, 1, is not in the loop, so it means it's don't care, so we need to use the flip-flop input equation to find its next step. And this one is our state diagram. And now we will use the circuit to prove our state diagram. And now I will show the result of the next step for A, B, C. Now the input is connected to the clock, so the output will generate itself. And now I try to change the clock to the input so that we can manually see the output, control the output. At the first is 0, 0, 0. Second is 0, 1, 0. Third one is 1, 0, 1. Fourth one is 1, 0, 0. And 1, 1, 0. 0, 0, 1. And it returns to 0, 0, 0. And this proves our state diagram. Thank you. And now we are going to show the state CBA, which is not in the loops, which is 1, 1, 1 and 0, 1, 1. Now CBA is 1, 1, 1, and the ways we force 1, 1, 1 to follow transition states is we force KA and KB becomes 1, and we press, then it will become 0, 0, 0. And another value, which is 0, 1, 1, is also not in the loop, and the ways we force it into the particular value is force Ka and Kb is on, and click this one, and it will returns 100, and that's for our part 1.
This is part 2B circuit. So this is 74HC151 IC, and this is 74HC00 IC. This is to replace the NOT gate. This is the multiplexer function implementation table that we built. So according to the table, input 0 is equal to 0. Input 1 and input 6 is equal to D. Input 2 and input 5 is equal to 1. And the rest, input 3, input 4 and input 7 is D prime. So the circuit is like this. According to the circuit we drawn, the select input 0 is connected to C, selected input 1 is connected to B, and selected input 2 is connected to A, which is represented by 3 of the switch here. So next we will test with the circuit. When all input is 0, the lights, the LEDs doesn't light up. When D is 1, the LEDs doesn't light up. When C is 1, the LED is off. When C and D together on, the lights on. And B, the lights on. B and D, the lights also on. B and C, the lights also on. When B, C, D is on, the lights off. When only A, the lights on. When A and D, the lights off. A and C, the lights on. A, C and D, the lights on. A and B, the lights off. And A, B and D, the lights on. A, B and C, the lights also on. And if all inputs is on, the lights off. This is our part 2C circuit. So this is 74HC138 IC and 74HC10 IC. So according to the Kmax, we have the equation that's formed and the truth table, and this is the circuit. The output Y2, Y4 and Y5 is connected to the LED using 3 input NAND gate, and the address 0, address 1 and address 2 is connected to switch A, B and C. So now when all A, B and C is off, there is no the LED is off. When C is on, the LED is also off. So when B is on, the LED on. When B and C is on, the LED is off. When A is on, the LED is on. A and C on, LED is also on. And A and B, the LED is off. And when the 3 of them is on, the LED is off.
This is our schematic diagram for part 3 circuits. We construct a K-map and we found that
between here and here, there are static 1 hazards.
This is the actual circuit for our part 3. We use one 74HC02 IC and one 74HC00 IC. We connected the input to the clock module and with the two outputs to the oscilloscopes. The following is the display that is shown on the screen of oscilloscope. When it reaches the falling edge of the input, the output value will suddenly drop from 1 to 0, and this is the static 1 hazard.
This is circuits we construct to solve the static hazards. We just add a NAND gate to the original circuit and we change this one into 3 input NAND gate and the static 1 hazard is solved.
This is the modified circuit. We just add a 74HC10 IC into the previous circuit, and from the oscilloscope we found that the static 1 hazard has been solved.